Video lecture 19E, the electrolytic cell and the electrolysis of molten ionic compounds. So far we've looked at galvanic cells. In a galvanic cell, we use a spontaneous redox reaction to produce free energy. This free energy can be used to push electrons through a device in order to power it. But what if we could hook up this galvanic cell to another cell to cause a non-spontaneous chemical change? This is the basis behind electrolysis, where we hook up a voltage source, usually a power supply or battery, to a cell to cause a non-spontaneous redox reaction. Electrolysis has a lot of applications. For example, electrolysis can be used to make free metals from very reactive metals. For example, the cell on the right is a cell used in the production of aluminum. This process, known as the Hall-Héroult process, involves molten aluminum oxide mixed with another ionic compound called cryolite in a cell that uses graphite electrodes. In this cell, aluminum 2+ or 3+ is reduced to aluminum solid, which settles to the bottom and is siphoned off out of the cell. We can also use electrolysis cells to refine metals. For example, to purify copper, we could use an electrolytic cell that has copper electrodes, an impure copper anode, and a pure copper cathode as a seed in a solution that contains copper ions. When the cell is run, purified copper metal plates onto the pure copper cathode, thus purifying the impure copper anode, which is destroyed in the process. Finally, electrolysis cells can be used for electroplating different metal objects, like silverware or jewelry. How does an electrolytic cell work? Here's an electrolytic cell that involves molten sodium chloride. The ionic compound needs to be molten so that the ions are free to move. A battery is hooked up to two inert electrodes in this case, and is then turned on. When a battery is turned on, it's used to pump electrons from one electrode to the other. The electrode that has electrons pumped away from it ends up being the anode. This forces oxidation at the anode since the electrode is depleted of electrons. Electrons will be produced there. Because electrons are pumped away from the anode has a positive polarity. This is different from the galvanic cell, where electrons are produced and gather onto the electrode. In this case, the positively charged anode will attract chloride ions, which have a negative charge. These chloride ions will end up being oxidized at the anode. On the other side, the electrons are pumped towards the now cathode, giving the cathode a negative charge. Since the cathode will have a negative charge, sodium ions will migrate towards it because of the opposite charge. And at the cathode, you'll end up with the reduction of sodium ions into sodium solids, which will deposit and cake around the electrode. The overall reaction here is that sodium chloride liquid is decomposed into sodium solid and chloride. This is a non-spontaneous change, which you can test by calculating an E cell for these reactions. Therefore, the free energy produced from the battery has caused a chemical change.